So we are live now on YouTube.
Thank you so much. Just 1 minute. Professor Abhishek is calling me.
Good evening, Professor Pant. I hope I'm audible.
Sir, you're audible, loud and clear.
Okay, good.
Yeah, go ahead. You are audible loud and clear. So please go ahead. Just give me 1 minute. I'll welcome everybody formally.
Sure.
There are around 16 people in the meeting, apart from 4 of us. And others are slowly joining in. So I think without wasting any further time, I will request Professor Abhishek from IIT Kanpur to start the webinar. And I will be there online for any, I'll be monitoring the chat window. Yes, absolutely visible. No problem.
Okay. So let me make it full screen. And so
yeah, now you are full screen.
Yeah.
Yes, please start. Thank you.
All right. So good evening to everyone who has joined this meeting. So I'll just present some of my thoughts regarding the design of VTOL air ambulance. Although, I mean, that is the focus, I'll take an example of a simpler platform rather to give you the whole strategy, the way it is actually done for these small vehicles. But I'll just give you a quick overview of, I mean, what kind of air ambulances have been there in operation for some time. And I request people to mute themselves. Right. So this is the overview of the presentation. So let's move ahead. So just look at the nomenclature of I mean, what kind of platforms are used for this air ambulance application. Okay. So it's the nomenclature that I mean I could find on net is actually a medically staffed and equipped air ambulance provides medical care in flight, while a non-medically equipped and staffed aircraft simply transports patients without care in flight. So the problem statement that has been given to you is actually staffed and equipped air ambulance. Okay. So that's actually a proper air ambulance. And as per NATO terminology, they call it medevac and casevac, where there is a casualty evacuation or medical evacuation. So you are trying to transport somebody from one point to another, but he needs medical attention all the way, and that's what they call it actually. Traditionally, almost all air ambulances around the world are actually helicopters. One of the old and famous helicopters is this MASH unit, Mobile Aerial Hospital, something they was called in Korean War, where this old Bell helicopter was actually sort of fitted with this kind of system to help it carry patients from one point to the other. Then Huey UH-1 actually was used for this purpose quite a bit, and then now several different other helicopters. This is Augusta Westland design. So this was model 47, and many other designs actually have now been put to use for air ambulance applications across the world. Even they get used for search and rescue kind of scenarios. I myself was actually part of this search and rescue helicopter design, where also we actually had to carry two patients in some sense, or people who are injured, and provide them some key medical care facility. And we actually had provisions for having defibrillators and some other equipment to give aid to the patients, I mean, on the while they are being transported from a point from where they are rescued to the nearest hospital. Actually, there was another competition. So this was actually when I was actually a student, and I participated in 2004, where we won first prize in VFS design competition. In 2019, there was a similar competition where one has to design a rotorcraft capable of performing rescue missions at highest altitude in the world, that is at Mount Everest, with a payload of 575 kilograms. And the mission should have been less than 3 hours, and also included a possible refuel stopover. So this was actually the design which won this particular competition. And this was again a team from Maryland. Some of our students from IIT Kanpur, like Abhishek Sastry, was part of this particular design competition, where they designed again a helicopter for this search and rescue mission from such high mountainous areas. So requirements for ambulance, I mean, of course, you have already been given a list of some equipment which has to be put in. So these are typical items for rescue. But in this case, I mean, your goal is to mostly transport patients and not necessarily carry out rescue operations. So these may not be relevant for you, but nevertheless, these are a few things which actually we had considered for our search and rescue platform development. Now the question is that, I mean, why we cannot keep using helicopters, and why do we have a need for designing a eVTOL air ambulance? Okay, so I'll just quickly touch upon that. The reason being that helicopters are very expensive equipments, both to own as well as to also operate over longer periods of time. So it actually has high operational cost, high maintenance cost, and it is somewhat sustainable across the world, because, I mean, other places, I mean, people are able to afford it. But here right now, I mean, you see, air ambulance can only be probably afforded by rich people like cricketers, film stars, and so on. Okay. So how do we make it accessible to common man, people like you and I? Okay. So that's why the idea is to come up with eVTOL solutions which become more affordable and simpler solutions, and come up with. So now, if you do a Google search, and I'm sure, I mean, because you are already in a somewhat advanced stage of the competition, you would have probably looked at so many designs out there. If you do a search on eVTOL on Google or any other platform, you will be thrown with, I mean, several hundreds of unique designs out there, okay, for eVTOL platforms, and there are so many of them. How do you decide which one actually is going to work for you best, and which one, I mean, you should avoid? So it's a very tough task. So, but let's first understand what is a eVTOL. So vertical takeoff and landing aircraft propelled by electric drive and capable of carrying people is what people are calling eVTOL, or electric VTOL. It doesn't mean that, I mean, if I use a onboard generator and engine, it doesn't become eVTOL, or it's no longer a eVTOL. It's still eVTOL because your main propulsion system, for example, rotors or these ducted fans, propellers, are still having electric motors, and the way they receive power is actually by electric means. So that's what makes it electric. Even though, I mean, you may have a fuel cell, or you may have a diesel power generator, or whatever, I mean, any other power plant to generate the electricity. And in this entire scheme of things, the key driver, I mean, why this actually is possible, I just quickly touch upon that, is because now it is possible to have these permanent magnet motors. So what you know as BLDC motors, brushless DC motors. So these motors actually are very lightweight, and this is what actually has driven this, and it is now possible to design aerial vehicles which are powered by electric motors. Okay. And second is, of course, the battery capacity. So this is a graph which actually gives you an idea of, I mean, how the battery technology has been changing. So starting from nickel cadmium rechargeable cells, nickel metal hydride, and now lithium polymers and lithium solid state batteries. So this actually has come up by leaps and bounds. So now, I mean, you can easily buy battery systems which can give you 200 watt-hour per kg to 300 watt-hour per kg. So already you can actually get batteries which will give you 250 or odd watt-hour per kg. And the world is moving towards, slowly moving towards 300 watt-hour per kg, but it will take some time. Okay? It's not entirely achieved and not readily available. So as they say, I mean, if Moore's law actually governed the chemistry of batteries, I mean, you would already be gone out of this graph actually, and we would have reached 400 watt-hour per kg or something way earlier. But that's not the case. The evolution of evolution of battery technology is way slower compared to other technologies, some other competing technologies which we are dealing with. So motivation is promise of new urban aerial mobility and use of applications such as healthcare and saving life. Idea is that this eVTOL system should be easy to fly, and you come into area where you can actually vary your RPM. So now with electric motors, what I can do is actually I can change my RPM, and as a result I can get control from that. So I no longer have to actually work with saw split, which is conventionally there in helicopters, and that actually adds to weight. There is also gearbox. Can we reduce the gearbox and make it lighter? So all those things are being looked upon now. And most importantly, because of this kind of electric VTOL technology, I can introduce autonomy, which is coming from the drone side of things. And with this autonomy, I can make this ambulance, which is autonomous to operate and doesn't require a pilot as such. So you only have a paramedic, which actually you are supporting. So early days of eVTOLs, you had people mostly trying to convert existing helicopter designs to electrically powered helicopters. And this was something similar was done for Yamaha RMAX helicopter, where they converted it from engine-driven system to electric motor. And recently there was a news, I think sometime back, there was a news where they actually used it for transportation of organs. And they could achieve a range of 30 nautical miles at a speed of 80 knots. Way back in 2018. And some other similar efforts have been going where people are using axial flux BLDC motor. Here they have used this YASA motor, and some other concepts have been tried. So now what happens actually, this almost all eVTOL designs actually is using multiple drives. That is, there are multiple motors, multiple propellers. In the center, you see this Volocopter by this German company, which has been around for a long time, 4 or 5 years actually. But this is one design. Then the Finmeccanica, they had this tilt rotor vehicle, which they have built long back, actually Augusta Westland, tilting ducted fan design actually. Then Lilium Jet actually has been around the corner for quite some time, and they have now done full scale trials also some time back actually. So there are so many options available, and key thing to understand is that the reason why you have to go with this distributed propulsion kind of architecture or having so many this small thing is that the moment I go for smaller number of motors, so people tried with helicopters, but the challenge with helicopters is that what happens, your here the power loading is low, and the torque requirement is very, very high. So with a single rotor, my torque requirement becomes so enormous that my motor will become extremely heavy, and because of the low RPM requirement, that means I will still need a gearbox. So if I do a direct drive, I require a humongous motor, or if I don't do that, then I still have to use a gearbox. So that is the challenge with single rotor design. So what happens when I go to multiple rotors, I can use smaller motors with much lighter weight because the torque requirement comes down dramatically here. So in this case, the torque requirement is order of 5,000 Newton meters actually. While here for smaller systems like this, Volocopter, etc., the torque requirement is much lesser, of the order of 100 to 500 Newton meters. That makes the motor significantly lighter than what it will be for a helicopter kind of design. So there are so many these configurations which are available, so these are normal conventional solutions like helicopter kind or multi-rotor kinds, which or flapping wing kind, which allows you to do VTOL. Beyond these typical concepts, there are hybrid concepts which tries to merge the best between the rotary wing and the fixed wing world. So you have fixed wing systems which has the major problem is you cannot take off and land vertically, and that's why you want something which can take off, land vertically, and do VTOL. So that is achievable through rotary wing systems, but they suffer from problem of poor endurance and high noise. So how do we combine best from both the worlds to get good efficiency in forward flight, but at the same time, have ability to take off and land from any unprepared runway and small areas. So there are many hybrid VTOL concepts, tail sitters, this lift cruise kind of platforms where you have a multi-rotor stuck to a fixed wing vehicle. So all of them actually has some pros and cons. There are many tail sitter designs, but then you can imagine these tail sitter designs are not suitable for the application that you are looking at. So there are many tail sitter designs out there. So for you, the better solutions could be this lift cruise designs, you have tilt rotor designs or tilt wing designs, which are out there. Some more designs like this. The tail sitter again is not very relevant for you, but tilt rotors like these, like quad tilt rotor or compound helicopters, where you have wings and rotor and propellers, all of them coming together and giving you a high-speed helicopter. So these are also something which may be of consideration. There is a company in US. Earlier they were called Cartercopter, and I think now they are called Archer or something. They actually are making a eVTOL platform, which is actually like a compound helicopter. So what is a compound helicopter? It is a helicopter where you slow down the rotor and you have additional wings and propellers to give you forward flight cruise and in a more efficient manner. But you have the luxury to take off and land and also maneuver using the rotor power. So this is a quick summary of how this kind of systems look or work. Okay. So your classical rotary wings, which are the helicopters and multi-rotor types, these would always suffer with efficiency issues in forward flight. You cannot fly very efficiently in forward flight, and these more so. Multi-rotor vehicles would be worse design actually, because they will have huge challenge when you scale them up, and that is why you see this volocopter has been around for a long time. Then similarly, this EHang, their vehicle has been around for a long time. But those vehicles again, suffer from poor efficiency, and that's why you have to go for some VTOL system which may be combination of these different ideas. Okay, so you can separate them out as lift and cruise designs, so that it brings in compound helicopters and these quad planes where you have multi-rotor. So this is Cora, Google Cora design, where you have how many? 6 here, 6 here, 12 propellers supporting the takeoff and landing, and 1 propeller for cruise. So you have separate propellers for cruise and for lift. Then the common propulsion systems are there, which are like tilting rotor, tilting wing, and rotor designs where wing and rotor both are tilting, or tilting body designs, such as this is a manned vehicle built by a company called Opener, and it's called Blackfly. So these are so many options out there. Now, from this, based on your requirements, one can go and look at and try to choose which configuration works best for you. So here are some of the videos. I'm sure you have already seen these. I'll just quickly play them for you. Okay. This is a design, one of the earlier designs by EHang, Chinese company. It has been around for a long time. Now they are even trying to enter the air ambulance market space. But then it's quite expensive. Efficiency and range wise, it is very limited. It can barely go 40 odd kilometers actually one way. This is Cora. So this is your lift cruise design. The Lilium jet actually has this similar, where you have tilting ducted fans which are attached to the tip of the or the trailing edge of the wing. So these are different designs which are out there, and people are experimenting. In Silicon Valley, there are so many startups. So this is just for giving you the background. This is the Blackfly design which I mentioned. Okay. So here you can see this is actually the unique platform, but again may not be best suitable for your requirements and design, because it's more of a recreational vehicle where a single person sits and flies. It does actually belly landing. Let me go to a point where you can see it. Yeah. So here you can see it landing like this. So it actually has a boat-shaped bottom, which allows you to land even on water surfaces actually. So this is another design like that. So now let us get to the more serious business. What are the issues that one actually has to deal with in designing a VTOL aerial vehicle? So in this, the goal is to achieve high hovering efficiency. So which is defined in terms of what is called figure of merit or power loading. Now these are some technical terms which I have to use, and I hope you are already familiar with that. Otherwise, you have to go and make yourself familiar, because unlike fixed wing design, you have to see how the performance actually is during the takeoff and landing phase, because that actually has a big impact on the overall design. The least amount of time you spend there and the least power you spend there will ensure that you have higher range. Okay. So that's why the efficiency in hovering and takeoff landing portion becomes quite important, and that is defined in terms of these. Then you have to also achieve high cruise efficiency, because now, unlike a fixed wing airplane, which has a very nice clean surface, now you have actually additional propeller sitting there, or more propeller sitting there, or there's some other mechanisms and complications, which is going to increase your empty weight and may also hamper eventually your L/D. So how do you achieve high cruise efficiency? That is the challenge. And third challenge which you have to deal with is, how do you ensure ease of transition from hovering flight to forward flight? Although it may be a control problem, but it is also related to aerodynamics. If you plan your design properly, the aerodynamic design aspects can actually aid the transition process. So this is something which one has to be very careful about. So here what I have done, actually, I put down some key design drivers. Okay. which may be relevant for a search and rescue kind of aerial vehicle. Okay. So this is taken from one of material design reports. So some of the parameters such as, so don't worry about the weight, this is for certain particular mission, but just to give you an idea what key parameters one has to look at. So hovering efficiency, ability to tolerate gust, what kind of downwash it generates when from where it takes off and lands. Okay. But it is search and rescue, not an air ambulance, note that. Okay. How agile it is in hover, how much CG travel it allows, performance in cruise, ratio of empty weight to the maximum takeoff weight. So sometimes, so it's like empty weight fraction. The vibrations that you face in the cruise flight, vulnerability to the ground crew, safe auto rotation, because aerial vehicles have some kind of built-in safety feature. So for helicopter kind of vehicles, it is actually auto rotation. Compactness, because you may have to take off and land from very small areas where having long wingspan may actually work against you and may not have a place to land. So compactness may be of relevance. And other things are, of course, life cycle cost, agility, technology maturity. So these are some of the just to give you an idea, like what are the key design drivers, what parameters one has to consider in selecting the configuration and then going about the design. Like how do you prioritize which aspects I have to focus on in my design? Other things are like noise, forward speed, and safety. So noise is also something very important. It's not part of this, but when you're going to rescue somebody from a busy city area, I mean, the noise may be a consideration. People may find it obtrusive. Speed is important because you have to, once you have the patient on board, you want to reach the destination, which is the hospital, in the shortest possible time, because that it could mean the matter of life and death for the person you are trying to rescue. And the safety of the vehicle, that may be very, very important in my opinion, because you are going to take off and land from unprepared areas where you may have trees around you, there may be people, I mean, nearby. Okay. So the safety of the vehicle, as well as the safety of the people around the area where the vehicle may be taking off and landing, may become also very, very important. So you have to consider about, I mean, how do you ensure safety? Maybe by hiding your propeller somewhere, ensuring that there is no vulnerable part which is exposed, and so on. Also, I mean, while you are designing things in India for Indian system, you should be aware of DGCA regulations. So right now, DGCA talks about these categories: nano, micro, small, medium, and large. This medium category is less than or equal to 150 kg. But then what you are going to make is definitely going to be more than 150 kg. So you are actually belonging to the large category, because what you are making is also a drone in some sense, or a UAV, but it will be inhabited with 2 passengers who are the payload in some sense. So you have to be careful about the regulations and keep an eye on that. I mean, how you are going to ensure that, I mean, certification and other aspects when the vehicle is designed. So total, what are the different aspects? You have design and development, you have aspect, and that's what, I mean, I'm going to come to soon in a moment. Okay. Other is actually the autonomy aspect, where you have to worry about the attitude stabilization and control, sensor fusion, navigation, basic autonomy like trajectory tracking, trajectory generation, path planning, enhanced autonomy where you do obstacle avoidance, object identification, tracking, etc., etc. So some of this may be relevant for you, but others may not be relevant for you, just to keep you informed. Okay. And yes, I mean, you have to worry about, I mean, high performance aerodynamic design if you want to ensure that good efficiency is achieved by your design. You are looking at the materials, I mean, what innovative materials can you bring in to ensure that, I mean, your vehicle is very, very lightweight and yet, I mean, gives you very good performance. Okay. So this design of this aerial vehicle actually is a multidisciplinary problem. Okay. And you have to sort of simultaneously target multiple aspects. You have to look at the aerodynamics, use the aerodynamics to calculate the performance, be it for hovering flight, be it for your mission flight, that is cruise, and you should be able to estimate the requirement of power for all those legs of flight actually. Okay. And right now, I mean, you already have idea about, I mean, what is the payload that needs to be carried, how long you have to fly to complete your mission. So that range is already known to you. So for you, the design drivers are, the key drivers are payload and the range. The time of flight probably is slightly less important for you. So here the configuration selection is very, very important. And I showed you various configurations, and probably by now you already know what configuration you are building. And you have to ensure that the configuration you are selecting is going to make your life easier in solving the problem that you are trying to solve. So there are different systems. So you have to worry about the sizing of structural systems, propulsion system sizing, avionics system sizing, and all of the weights actually has to be accounted for and finally included in your overall design size. So that brings us to the whole design, the way the design process works. So this is from where the more technical part starts. So first is, of course, you have to define the mission requirement. So which is known to you, which is been given to you in the RFP or the problem statement which you are working on. So there, where we talk about payload and travel distance. Now, based on the design drivers, by now you should have decided upon which configuration you are going to build for meeting the mission requirements. Once you know the configuration, in the configuration you have to make the key decisions or key choices you have to make. So this key initial choices would include, based on the configuration, whether it is a single wing design or it's just a multi-rotor design or it is a tandem wing design. So depending on that, you will decide number of wings, geometry of wing. You will decide the number of rotors that you are going to have, whether you have separate rotors for takeoff landings, separate rotor for propulsion. So depending on your configuration, so all these choices have to be made. While making these choices, two key parameters come into picture, two key design drivers. One is your disk loading of the rotor, which is being used for vertical takeoff and landing. That will actually determine your power consumption during the hover and takeoff landing phase. You may think that takeoff landing phase may be very small, but the initial phase actually ends up consuming a lot of power at certain times. So that actually becomes one parameter. The second parameter actually, and that actually also sizes your motors and propellers, which actually would be used for vertical takeoff and landing part. The second part actually the cruise part. So for that, again, the wing loading becomes a key parameter. So when you are deciding these initial parameters, you will normally specify the disk loading for your lifting system and your wing loading for your cruising part. If you have a hybrid system where you have propellers which are allowing you to do vertical takeoff, and you are actually supporting your weight during the forward flight. So you decide all these initial parameters, and right now these initial parameters would be based upon existing designs or your some experience or some basic simple quick calculations. With this initial geometric information and other parameters, you start by guessing the weight of the vehicle. How do you guess the weight? So that's where you have to see what is the typical payload fraction currently for VTOL vehicles. And it actually is not very, very promising. See, for example, if I use a helicopter, my helicopter's payload fraction could be as high as 0.4, 0.45 and thereabout. But when I come to a VTOL vehicle, for example, I use a biplane tail seater or a tilt rotor or a quad plane. In each of those designs, what happens, my payload fraction, which is the ratio of your useful payload to the gross takeoff weight, that drops down to 0.2 to 0.25. So that is the most optimistic value to choose. So for example, if I have to lift 200 kilograms of payload right now, my overall vehicle weight is going to be more than 1,000 by all means. That is a conservative. It may end up becoming slightly higher also. So realistic payload fraction would be of the order of 0.2, I would say, to start the initial calculation for these kind of vehicles. So with that, you have some idea. Okay, so I have to lift say 200 kg, and maybe I'll say okay, my overall vehicle weight is around 1,000 kilograms. With that, I start the power calculation. So this power calculation is actually important. So you have to do power calculation for hovering flight and for climbing and for cruising flight. So you do the power calculation for different legs and use this power calculation to calculate the total amount of energy required for the entire mission. Depending on the configuration which you are choosing, you have to see how this energy is going to be supplied. Is it going to be supplied purely by batteries or by having a generator system which is consuming fuel, or using a fuel cell, or maybe a setup where I have a combination of a battery-based system plus fuel-based system, something like that. So all those things actually can be looked into. With this power calculation, where you do power estimation, torque estimation, RPM, etc., you specify that what is the RPM that I'm going to operate my rotor side actually. So with that, you will be able to get an estimate for what kind of power is required for selecting my motors. So this is where we'll look at a thumb rule. When we'll talk about that once we go to the take the example design of a small quad rotor. So here we'll estimate the energy required for the entire mission. So that will give you idea of, what volume of fuel I require, or what capacity battery is required. It will also help you size the motors in terms of, how much torque each motor has to develop, and what kind of kV can I work with, depending on the voltage that you've chosen for your power plant. So once you do this, some detailed calculations regarding energy requirements, your current, how much current motor will require, each motor will require, what kV the motor will operate at. So based on all this information, you would then be able to do some weight estimation. And in weight estimation, we have to estimate weight of each and every component. But how do you do that? Because you have not built the vehicle yet. So for this, typically there are a lot of these formulas available, empirical formulas for designing. So there are formulas available for designing helicopter kind of vehicles. There are formulas available for designing airplane kind of vehicles. For example, all of you would have seen the book of Raymer that gives you formulas for designing or estimating weight of. So there is a formula to estimate the wing weight. There is a formula to estimate the airframe weight, landing gear weight. Likewise, there are now there are research papers also, there are theses also, and then there are books like Raymond Prouty's book on helicopters, where you can find formulas for estimating weight of the rotor, weight of the, if you are going with a helicopter kind of design, sauce plate weight or landing gear weight. So you have to now go and pick and choose from different sources and try to come up with some kind of formula to estimate the weight of each and every component. So for many of these things, you can easily get formulas from different sources. Finally, weight of wiring, avionics. So each component that is going in the entire vehicle, including the payload, battery, electronics, and furniture, whatever is there. Each and every weight, the weight component of each and every thing has to be estimated somehow, and then finally be added together. And then with this total added weight, we have to see where you stand in comparison to the initial guess that you had made regarding the weight. So when you compare and see if this is actually close enough to what you guessed initially, then you say, okay, fine. I have come up with a design. Okay. But if it is not the case, then whatever new weight I have gotten, I will use the same weight and redo the entire power calculation. And this keeps going on iteratively. So you have to understand that the design process is actually an iterative process. The design doesn't happen as open-ended system that, okay, I get some numbers and I do some calculation and I get a design. Yes, you can get a design by doing one set of calculation, but that design is not necessarily optimal. You have to come up with a set of designs. So normally what happens, you end up writing a code for something like this, where you have all these formulas in MATLAB or any programming language. And by running this code, by changing the initial parameters which you have decided or guessed or chosen, I would say, in the beginning, you can generate hundreds of designs. Out of these hundreds of designs, you would finally zero in upon the design which appears to be the lightest design possible among all that you have designed. And that actually would be the design which you would start with and start analyzing in good detail. Sometimes this loop may not converge, and that implies that you are probably giving some input incorrectly. You are giving some input for which the feasible design is not possible. It is going beyond normal things. So this is the overall flow chart for designing aerial vehicle, a VTOL aerial vehicle. So in this, you have to have formulas for. So the approach is same for a fixed wing or a rotary wing, just that because if you're going with a hybrid vehicle for a eVTOL, you have to bake and borrow things from fixed wing world and also the rotary wing world to combine it and come up with a meaningful process by which you can get good estimates of these components and be able to come up with a design. Another key challenge in this is, how do you do the power calculation? So power calculation part actually is slightly tedious and tricky, but then you are already familiar for power calculation for fixed wing mode. So when you're flying in the fixed wing mode, your power happens to be your drag times velocity. Okay? So that gives you the power in forward flight. But in the hover part, okay, when you take off and when you are climbing, your vehicle is mostly working like a helicopter or like a multi-rotor. So in that case, what happens? You have to use simple theories like momentum theory, or you can use blade element momentum theory to estimate the power that the system will require. So momentum theory is probably the easiest approach, in which you simply your power, ideal power, becomes equal to thrust that you are getting from each rotor to the power 3/2 divided by square root 2 rho A. 2 times density into the disk area of that rotor. So if the rotor is generating T thrust, the power is given accordingly. It's there in all books actually on helicopter theory. I mean, you can easily find that out. So that's why I have not put it here. But that is the only ideal power. How do I convert that ideal power to a real power? So what happens, I mean, we are going to use some propellers on these, which will be having a particular efficiency. So this efficiency of hovering rotors is defined in terms of, or propellers is defined in terms of figure of merit. So this figure of merit for the kind of scale of propellers you will be using would be of the order of 0.7 to 0.75, somewhere in between that. And that's what you can use. So ideal power that you get, if I divide it by 0.7, 0.75, I will get a good estimate of how much is the actual power required. But beyond that, there are more advanced techniques like blade element momentum theory. One can do CFD, and BMT is also very easily doable. One can write a simple small code, and all these are readily available in books on helicopter theory. So, like I already mentioned, the weight formulas have to be now sourced from different places. There are research papers also where people have given these weight formulas for designing your eVTOL systems. So that brings us to so this example problem, okay, where I thought I'll explain to you the whole process and how this entire thing is done by taking the example of a simple multi-rotor. Simple multi-rotor is actually also a VTOL vehicle, and it has motors, propellers, and ESCs, etc. So this is the process which is followed to design this. This is taken from a paper by Winslow and Rishikesh. It's from Journal of Aircraft 2017, and it outlines the entire algorithm where you can do a closed loop design of a small quad rotor. And this is the process which you have to follow exactly, or ideally you should follow exactly when you design your VTOL system, because it's an electric based system. So you have to have means of calculating different component weights and so on. So like we discussed earlier, we start with the inputs where we have giving the flight time. In our case, it may be range. Then you have to make selection. If it's a purely electric driven system, you require to select number of cells. Then you decide, I mean, the rotor's radius, solidity of the rotor, number of blades in the propeller. You have estimated or guessed the gross takeoff weight, and you know the payload. So with payload and range and other parameters, you will be able to initiate the whole power calculation process. So that's where this blade element momentum theory comes into picture. So you have a module which calculates the power. From this power, and because you know the number of cells you are using, okay? So I know number of cells. So lithium ion battery or lithium polymer battery, each cell gives you 3.7 volt. So you can use number of cells in series and parallel. So if I stack multiple cells together, like for example 6S, okay? So 6S means, I mean, 6 into 3.7, so that is the nominal voltage. So depending on that, I mean, I know what is the voltage available. So once I know the power that is required in my hovering flight, that power required divided by your voltage will give you the current required. So some of those, so V is already known to me. I mean, what is the voltage that is available, because I know the number of cells which I have selected actually for my design. And I have already calculated the torque, the power, and the thrust. And I have also made some choice for RPM, okay, because I have to say, okay, the nominal RPM where I'm operating at is this actually. So from that, I know my voltage, and I know the power. So power divided by voltage will give me the current requirement. Okay. Now this current requirement has to be used to size my motor. So what do we mean by size my motor? So let's take an example. I have a multi-rotor, and this multi-rotor is say a quad rotor, and the quad rotor weighs, for example, say 1 kilogram. So now when I am doing hovering flight, each propeller is, or motor propeller combination is delivering 250 grams of thrust. With this 250 grams of thrust, okay, the power required is say so many watts, okay, say 120 watts or something. And that is what the power that is required for hovering flight. But now when I have to choose a motor, what am I going to do? Am I going to select a motor which exactly gives me 120 watts of power output? Or do I choose a motor which will give me 130 watts of power output? Which motor do I go and choose? That's where you have to apply a thumb rule. And this thumb rule is for the convention. Even when people were designing an eVTOL vehicle like Vahana, which was done by Airbus, there also they use the same idea. So if I require, say, thrust of, so in my multi-rotor case, 250 grams, I will actually size it or select a motor which is capable of delivering 500 grams of thrust. Okay, so it has the power capacity to handle double of what I require in normal hovering flight. So question is, why is that? I mean, why do I actually have to put a motor which actually is going to deliver double the power or double the thrust, rather not power, double the thrust that I require? And the answer to that is, when you are in hovering flight, there could be wind, there could be gust, or otherwise, I mean, from hover, I have to maneuver, and to keep the margin for this extra disturbances, to reject disturbances or fly at particular speeds, we keep extra margin, and that's why we size the motor to have double the capacity of the thrust that it can deliver in hovering flight. So now what I do, like I said, I mean, if I have 250 grams of thrust requirement, I will have some power requirement. But what I will do is that actually I will say how much power is required to generate 500 grams of thrust. So simply by using momentum theory, I can do T to the power 3 by 2 by square root of 2 rho a divided by some figure of merit, and I'll get some power. So that power is now the max power that the motor should be able to deliver. And I will select the motor which meets that kind of power output requirement. And with that power, I divide by voltage and I get the maximum current. And this maximum current actually is used to now estimate the mass of the brushless motor, estimate the mass of the ESC. So how do you estimate? We'll see that in the coming slides. So you estimate these component masses. Then in addition, we have the overall requirement of flight time. So we can, once we know the power required, we can see the energy requirement. From energy requirement, we can estimate the mass of the battery that is required. In this case, it's a purely battery powered vehicle. How do we get the mass of battery? Because in the earlier graph you saw, we see that current battery technology is typically around 250 watt-hour per kilogram. So every kilogram of battery will give you 250 watt-hours. So based on that, actually, I will be able to estimate my battery mass. Then there are other empirical formulas to get the mass of the rotor. So this mass of the rotor plus mass of the battery is combined, and estimate of the airframe mass is made. So all this actually is put together. So once I know, I mean, how much is the battery mass and how much is my other rotor mass, etc., and motor mass, I will be able to estimate the mass of my airframe. So now I have mass of my airframe, mass of my rotor or propellers, mass of my battery, ESC, the motor, and then you add some additional mass, I mean, some small fraction towards avionics and other components, which could be 5% of the entire mass for such small vehicles. But it could be also actually estimated and put as a fixed mass, which is there for, say, you know, which autopilot you are going to use, you know, the mass of that, you can put that indirectly. And then some small fraction has to be added towards wiring and other considerations. So we add all these masses of all components and get the sum total mass. And here we see whether this actually is less than the previous guess value. If it is, or it is coming close to the previous value. If it is not, then we actually update things and we update the mass and redo the entire calculation. So we increase the gross takeoff weight and redo the entire calculation. In this, I mean, there is another decision making which was done, which I did not mention and I skipped sort of, is that if it's a very, very small multi-rotor, sometimes you have to take a call on whether you are going to use a ELDC motor or a normal brushed DC motor. So that is only for very, very small systems. I mean, brushed DC motors are recommended. Everywhere else we use BLDC motors. So this is the overall flow chart of how you actually go about doing the design process. So this is an example. Similar things have to be created for your own design process that you will have. So this is actually related to power estimate, and this power estimate directly drives the weight of key critical components like your motors, like your propeller sizes, propeller weights, etc. So let's look at the derived parameters again. So we use power for from BEMP and initial selection of number of cells in battery pack to find the current. So you have to know the current, but the motor are to be sized based on the highest current expected, which I already mentioned. So normal thumb rule is that we take twice of the gross takeoff weight. So max current corresponds to situation with maximum power. Thumb rule is to find maximum power for thrust that is corresponding to twice of the gross weight. So I said, I mean, if my in nominal condition, if my propeller requires 250 grams of thrust for my 1 kg quad rotor, I'll select a motor which is capable of delivering 500 grams of thrust. Okay. So that is the idea. And then this Imax, which you calculate, is used for sizing of all power plant, motor, ESC, everything. You will select ESC, which can deliver this max current. Okay. and not what you actually require for hovering flight. So if I require for hovering flight 10 amperes, I'll choose a ESC which is actually capable of giving me maybe twice of that. But actually, we have to look at Imax and not just directly do twice of whatever is nominal. So, like I mentioned, weight estimation of all components is through empirical formulas, which is typically obtained using some kind of regression fitting on available data for existing systems. So, the paper I mentioned by Winslow and Chopra, in this paper, they actually bought or collected data for, large number of motors available in the market, large number of propellers available in the market, batteries, ESCs, everything. And they were able to finally come up with, so this is the data which they could contain or obtain in terms of actual weight and the predicted weight. And with this regression formula, they created this regression formula from this. And they are showing how accurate this regression formula prediction is compared to the actual data that you have. So this is actually for very small motors, remember that. So you cannot don't try to use these formulas for your calculations. This is only a representative thing to give you the process. So sometimes you may not get any formula for something, and then what you do, you try to collect data for things which is available in the market as much as you can, and then you create your own formula using that regression fit like this. So here they put rotor weight as a function of your radius of the rotor, solidity of the rotor, which is the blade area by the disc area, and the number of blades. So these three functions are three parameters are there, and as a function of that, they are able to derive the mass of the propeller in grams. The battery weight trends with energy capacity and the number of cells. So similar kind of thing was done here, and where C here is the capacity of battery in milliampere hours. It's a small system, so you don't talk about ampere hours, you talk about milliampere hours. And S is the number of cells which are in series. So that actually gives you, if I have 3 cells, 3 into 3.7, 11.4 volts there. So, or sorry, 11.1 volts rather. Also, you have to be careful that whatever is given in mAh, how do you convert it to watt? Because mAh is actually not a unit of current, it is actually unit of power. So how do you convert that? So milli 0.001, S is number of cells, 3.7 is the voltage per cell, and then 3600 for the second to hour conversion, and whatever is given in mAh. So if it is 5000 mAh, you will put 5000 here. So you multiply this, and whatever you get is actually that much of watt that it can deliver. So some more details about, how this C rating. So these many batteries actually have this C rating available. One, it is like a continuous C rating, like how quickly you can actually discharge the battery. So now any battery has a typical energy content. So energy content can be given as E equals to power that you are extracting from it and the time of discharge. So one can say P by E is 1 by time of discharge or 1 by hour. And this 1 by hour, what you get is actually called C rating. So if I take a battery and I sort of extract current from it or take energy from it at a rate such that it actually drains out in 5 hours. The battery completely drains out in 5 hours, then it has a rating of 1 by 5, C. The same battery, if I extract current from that in a way that it actually drains out in 1 by 5th of an hour, then it is rated 5C. Okay. Or same battery, if I can completely empty it in say 1 by 40th of an hour, then it becomes 40C. That is the whole idea. So it actually is sort of representative of how many cells are there in parallel, and as a consequence, how much max current can you draw without damaging the battery. So it is important to see the C rating of the batteries also. So the relation between the current and the C rating. So like we see, P by E is 1 by time of discharge. I can put I into V up and down, and this IVT is the C or the capacity in ampere hours, and so this is I by C, same thing, and this relates to the C rating. So current that will discharge 1/5 of the capacity in an hour, so this is 1 by 5C, and then 5 means I can the current that actually discharges 5 this 5 times 5C capacity in an hour. Okay. So it's the way how you interpret this C rating of batteries. So higher C rating means it can deliver higher currents. That's all I'm trying to tell you. Okay. So high C rating means high power and high current. So it can deliver higher power because voltage is same for both the batteries. And since I can deliver higher current, that means I can deliver higher power. Energy content may be same. So I can have two batteries, which both of which actually have say 10,000 mAh, but then one is 40 C rated and other is actually 20 C rated. That means 40 C rated can actually deliver double the power of the 20 C rated battery. So that you have to keep in mind when you are designing your system. Then look at the kV of the motor. So this is speed constant in revolutions per minute per volt. That is the definition. So it simply looks like, I mean, it is like RPM divided by the battery voltage. But then this is not entirely correct. So it is not, because what happens that, I mean, your BLDC motors, your RPM is not a function of your voltage. So I can give any voltage, but my RPM is actually controlled through PWM signals. So general definition is no load RPM of motor when 1 unit voltage is applied to the motor. But that is not entirely true, because that doesn't change the RPM. So in reality, this kV of the motor actually represents the back EMF voltage that motor would generate when it is spun with kV RPM. So what happens? I take the motor and say the motor is rated to 2300 kV. So if I take the motor and spin it at 2300 RPM and I measure the EMF across the two of the ports of the motor, I will get actually 1 volt back. So it is generating a 1 volt back EMF at this particular RPM. Similarly, say a 230 kV motor, that will actually, if I spin it at 230 RPM, I'll get 1 volt as output in that case. So the motor weight for BLDC motor actually scales with peak power. That is, what is the max power it can deliver, which is in terms of peak current and the kV. So in some sense, one can say that the power is actually a function of torque required, because the power output is your omega into torque also. So once you set the omega to a particular value, it is actually directly dependent on your torque. This is a very important part, because in your design, how you size your motor is very, very critical. I mean, yes, you can go and look for standard motors which are available out there, and you can see what is the rating for that, what is the weight for that. But then you need to have some kind of empirical formula in your design code, which will help you estimate this. And now there are some papers out there which you can search and find, where you can find these formulas which will allow you to size the motors. That is, if I give the power required, it will tell me how much my motor is going to weigh. So here is a formula which was used given in that particular paper. But remember, this formula is for very, very small, tiny motors, so one cannot rely. So here what they did, they said the motor, brushless DC motor mass is a function of the kV of the motor, the power output of the motor, and the current and the power, which in turn actually decides the length of the motor casing and decides the motor diameter. So what happens? These motors, I mean, to get the same amount of capacity out of it, I can have a taller motor or a fatter motor. So with a higher diameter, or a narrower motor but with a longer length. So depending on those two parameters, one can actually have same amount of power. And that's how they actually came up with this formula, where they said, okay, the motor casing length and motor diameter is dependent on this current, kV, and power. And once I know the current and the power, and this current is actually max current, I can estimate this L and D, which goes back in here, and from that I finally can get the mass of the BLDC motor. Similarly, they came up with a formula where they saw a direct relationship between the current, max current, that the ESC can handle, and with that they got a empirical formula to calculate the mass of the this ESC for the motor. So again, remember, this Imax is based on power needed for twice of thrust, where T thrust is the thrust required for hovering flight. Don't calculate power for the hovering thrust and double it. Always make sure that, I mean, you use the twice of thrust to recalculate the power, because it will have different implications. Then they came up with formulas for airframe mass as a function of radius of the propeller and mass of the battery that it has to carry. And with all that kind of things, they then actually went ahead and tried to do validation against existing designs. Okay, so they took various small designs with brushed motor or brushless motor. So they took this SIMA X8G, DJI Phantom 1, and they using that code which they developed, or the process which they developed, they did a validation. So you see the comparison of the rotor mass, which is actually measured on the real system, and how much it is calculated, and the kind of error you incur. But the interesting part is that, I mean, yes, there are errors at places. For example, there is a error in the ESC mass, which is somewhat significant, 33% error actually, because calculated is 27 grams and actual weight is around 40 grams. So even despite of some of these errors, it actually balances out very nicely, and the final weight of the actual craft and the final weight of coming from the design ended up being exactly same. And that is how it is. I mean, for the final gross take of weight, in most cases, we see very, very small errors. So you can, that kind of gives you confidence that these kind of approaches are fairly meaningful and really valid for engineering application, especially at the conceptual design stage, where you're trying to explore multiple design options and trying to find some unique solution or some designs which gives you an idea that, okay, when I select this set of parameters, my design actually may work for me and give me a lightweight aerial vehicle which will work optimally for my requirements. Some other things regarding VTOL. Okay. Okay, sorry, this, yeah, I don't know why these slides are again repeating. Yeah, so I actually wanted to show this last slide. Okay. So one major question which actually we'll have to answer is, do we have a larger number of, because in eVTOLs, I mean, every design you see out there, there are larger number of propellers. Nobody will come with a design where you have a helicopter with a single rotor, because if that was the case, then I mean, we'd not even be organizing this competition. So what you expect, this is again output of a design calculation where you are changing the disk loading. So disk loading is your thrust per motor by the area of the rotor disk. And with that, and in this case, I mean, the payload has been assumed to be around 250 pounds or 125 kilograms approximately. And this design study was done by somebody. And in there, they found that the weight, overall weight, if I use a single main rotor and then some 10% of power goes to the tail rotor, is the heaviest design in all. And if I increase to number of rotors to 2, I actually see that the design weight is actually significantly less. If I do 4, it is further less, 8, even less. So that is telling me that, oh, if I keep, so this is coming from the design code, if I keep decreasing, or rather, sorry, keep increasing the number of this propellers, okay, we keep increasing the number of propellers or rotors in my design, my weight will keep on decreasing. But in reality, in actual condition, this would not be true. The trend actually tends to get reversed. If I increase number of very large number of rotors and propellers, my weight tends to increase, or my gross takeoff weight will increase more. So question is, why does it happen? The reason is that what happens, I mean, when I start increasing large number of rotors and propellers, you actually end up having a lot of support structure. Each propeller has to be supported. It has to be rigidly attached to the frame, and that weight addition starts to increase. Further, when I go to smaller and smaller propellers, the aerodynamic efficiency also tends to decrease. So that actually drives my power slightly. My power requirement goes up slightly, and that actually adds to my battery weight. And in some sense, I mean, you finally realize that there is a optimal point where, I mean, with some number of rotors, you will actually be in a sweet spot where you don't have the penalty of, I mean, having to use a very large heavy motor, and other side you don't have the penalty of having too many small motors, which actually increases your airframe weight significantly because of the extra support structures, the way it is happening in volocopter and so on, where they have, I mean, I don't know, I mean, 20 odd or 16 odd propellers, and with that many propellers, you have so much of airframe which is to be added, and it adds to the weight, and it also adds to the drag. So your drag will increase significantly because of that. So that is all from my side. Okay, so that's what I wanted to give you a quick snapshot of the whole design process for VTOL vehicles. I mean, how a typical multi-rotor or a VTOL vehicle is designed, and I'll be happy to answer any questions that you guys have.
Wonderful, wonderful. So we will now open the floor to questions from the students. I'm in a slightly noisy area, so I'm going to just mute myself, but people will just raise their hands and I will unmute you. So if you have any queries, you have two options. One is you can type in the chat window, which I'm monitoring. And the second is you can just raise your hands so that we can unmute you. Okay, so we are waiting for your queries. If there are no queries, then we will
I
stop
think
the
there is
webinar.
one question or something, I don't know what it is actually about. There is something, you can change the dimension of a vehicle. 10 by 10 is too big.
So that I have responded, Abhishek. Actually,
okay.
I would like to clarify that we have given 10 by 10 as the maximum dimension or desirable dimension. If you make a smaller vehicle, we have no problem. So I have clarified to him that 10 by 10 meters is the desired maximum and 12 by 12 is the absolute maximum, not to exceed. But if you make it smaller, it's fine.
Okay, understood. Okay.
So I've been answering questions on the chat window while you were speaking.
Okay.
Now we will open the floor for any live questions anybody has. Okay, just raise your hands, guys, if you have any questions. We had a very detailed presentation, which is going to be available to you on YouTube. Okay. Samriddhi has a question. She says that since these are unconventional design methods, there is no guarantee that two different design methods will merge and will get the same sizing results. So how do you decide on the design method which we want to follow? So Samriddhi, I think when you are looking at unconventional design, you don't have any a priori knowledge. You'll have to just choose one method and follow it. Ashwini ji has raised the hand. Ashwini ji, we'll just try to.
I mean, if I can add to what you just said.
Yeah, please go ahead.
So Samriddhi, it's a very good question actually, and that is the risk we are, at in this design exercise. But what you can do is that, you can always do part by part validation to some extent. So if you have some particular method in your mind which you are following to design things, you can do a comparison and try to pitch it against some existing design. There are a lot of designs out there which actually has some information available on internet. So for example, you take a design of, Vahana. So you can try to test your design methodology by doing it against Vahana. So Vahana, they had released a lot of information in public domain. Or there are other designs also where you may get some information in public domain, and you can try to run your design methodology against those particular vehicles, and then you compare that whether at the end, are you able to get similar weights? So whichever method you see, is giving slightly better performance, you would probably want to trust that more.
Right, Samriddhi has said okay. Thank you so much. Next, will you be able to? Professor Kalpit Kaurase has a question which is not connected with this topic. So I would not like to open up the webinar for other questions. Right now, we are discussing only about electrically powered aircraft for the air ambulance for the NACDeC participants. We will not be opening the questions for other types of aircraft. In the meantime, I think Ashwini ji, you would like to speak. So I'll just unmute you. Ashwini ji, you can even open your camera if possible.
Thank you, Dr. Pant. Very kind of you to allow me to speak, because I'm not a designer and I'm not going to participate in the design. But my question to Professor Abhishek, first thing, compliments to Professor Abhishek for an excellent, detailed presentation. My question is a little generic, which is that we have named this as an air ambulance design or a search and rescue vehicle design, because air ambulance would be just to go and pick up an injured person and bring that person to the hospital, whereas search and rescue would entail a few other things. Search would entail a few more sensors to be put on board, which will increase the weight of the vehicle. So I guess if that is made clear, probably it will be better for the design teams. Thank you.
Sir, actually, that is already very clear, sir, that it's an air ambulance project. I just gave examples of, similar vehicles which have been designed in the past, which can act as a reference to students. Actually, that is all. The problem statement clearly outlines, what exactly is expected from them. And sir, actually, there is no such intention of using it for search and rescue. I just gave it an example as a passing examples for similar vehicles, which actually had, or a different scenario where, I mean, same vehicle may be able to meet the requirements in future.
Okay, thank you. Thank you,
Thanks.
Professor.
Thank you, sir. Thank you. So I see a question
On
from
the chat window, there is a, yeah, sorry.
right. So you're facing issue to find
If you can
aerodynamic.
read the chat, then you can talk yourself, I think. I don't have to intervene.
Right, sir. Right. Yeah. So aerodynamic efficiency and power consumption rate. I mean, Deepak, can you elaborate that? I mean, if you can unmute and speak or something. Okay. You are talking about aerodynamic efficiency of what? Are you talking about the efficiency of the rotor itself, or is it the propulsive efficiency in forward flight? What exactly are you talking about?
Yeah, so it may be a good idea for students like Deepak who have specific questions to unmute and speak. So Deepak, if you wish, I can unmute you. In the meantime, there are two hands raised, one by Malayajit. Deepak, would you like to unmute because this will take too much time?
Sorry, yeah, right. But he has typed, maybe he has some mic problem. So he has said rotor and propulsion efficiency for forward flight. So see, this actually is, you are saying, find the aerodynamic efficiency. I mean, see, these parameters can be actually calculated. And fine. So that's we understand. So this see, you can consult any book on rotary wing system, any helicopter aerodynamics book. That will give you very clear idea of how you estimate the performance in these conditions. So you can estimate the power required if you are rotor which is in edgewise flight, or if you depends on your configuration. So in forward flight, I mean, both for fixed wing and rotary wing, there is enough amount of information available in books. So consult some good book.
Hello, good evening, sir.
So Sovan,
Yeah,
would you like to speak?
Yes, sir.
Yes, sir.
Good evening. This is Malayajit. Hello.
Yes,
Yeah,
Oh,
yes, sir.
okay.
I have a question that I wanted to know that if I consider the helicopter, so whatever the power consumption, whatever the energy is required, whatever the size of the blades and all these things, can it be equivalent bifurcation in the eVTOL also? Means if I consider in helicopter one wings only, okay, and it is divided into 8 wings in the eVTOL, can it be equally divided as a power consumption and the voltage requirement on that, or there should be the energy efficient will be there for eVTOL?
Okay, I'm not very clear what you are actually hinting at.
What is the power? Actually, if I suppose I given an example, if suppose 2 kg of milk is there, I wanted to divide it into 250 grams in the each packets. So can it be if I consider that things in the eVTOL, the same power energy can be equivalently divided into eVTOL. So power requirement will be the same, or it will be less.
See, I mean, finally, you are talking about a vehicle which will have same takeoff weight, if we say. Okay.
Yeah.
And if you're saying that, I mean, the vehicle has same takeoff weight, and I lift it with 1 rotor versus I lift it with 8 rotors. Is that what you are saying?
Yes.
So the power required actually will not be the same.
Okay.
Because 1 rotor, I mean, your efficiency of the rotor will not be same for the smaller rotors and the larger rotor. And
smaller rotor.
In reality, what happens? I mean, if I go with the design with a single rotor concept or configuration, my final, I mean, all of it may come out to be very different from the weight which will actually be there for when you use a 8 rotor vehicle. So it is very difficult to say that, I mean, you can distribute the power like that.
Okay.
So it will, in all likelihood, it will not match actually. It will not be same. One of them will be more efficient, other will be less efficient. So that you have to calculate and see for yourself.
Okay, sir. Okay, thank you, sir.
Okay, so Sovan, I want you to unmute if you want to speak. So Sovan, please go ahead.
Thank you, sir. Sir, my question is like we have the design like if we want to reduce the area, then we can reduce the total area of our drone or vehicle. So in this process, the design efficiency, like aerodynamically, I'm not calculate it by the aerodynamically shape. Like I'm not giving it aerodynamic shape. if I sort the area, and if I make it longer, then I can calculate it by the aerodynamically safe also. So what is per what is like you prefer that it should be aerodynamically designed or it should be shorter in design?
I mean, you are talking about the footprint of the vehicle, that if you are going with a larger footprint, you can make it aerodynamically safe. But if you are going with a smaller footprint, I mean, you have to sacrifice on aerodynamics. Is that what you are saying?
Yes, sir. Yes, sir.
Okay. So that again is a trade-off. I mean, you have to see. Finally, it's a penalty, right? I mean, you have to see one extreme where, I mean, I make it very, very short and make it very unaerodynamic, right? So my power requirement may go up and I may find it difficult to meet my mission requirement. On the other side, I actually see, I mean, I make it very, very large, but then it may actually go beyond the constraints or the guidelines posed in the competition, that, I mean, it should not become bigger than this particular size, right? So, so keeping both these minds, I mean, you have to do the trade-off and see where you actually are happy with your, you are able to get both of, I mean, best of both sides. You are not becoming too large or you are not becoming too unaerodynamic.
Okay, sir. So one more thing, like our operation area is in the city maximum time. So what about the safety issues? Can you please elaborate something like the safety issues?
So safety, see, I mean, comes from two sides. One is, I mean, the safety of the people who would be around, I mean, when the drone comes and lands, right? So imagine, I mean, if there is a system where, I mean, you have rotors which are spinning and it's open rotor, and somebody by mistake falls on the rotor, okay, or gets in contact with the rotor and he gets injured himself, right? That is one aspect. Second is, when the drone is coming and trying to land, I mean, there is some tree in the neighborhood or something, and for some misfortune, it actually ends up colliding to a tree or some such thing. So the safety of the vehicle itself. So these are two different aspects. So normally people talk about ducted rotors, for example, which says, I mean, if I make the rotor ducted, it is covered. The chance of it hitting something or somebody coming and hitting that actually becomes much lesser or smaller. So this is one aspect of safety. Other could be the reliability of the system. Of course, I mean, once you make it and once you certify it and get it tested, I mean, it will eventually become reliable. So that actually becomes less of a safety aspect, because somebody may think that, okay, some technology is mature, some technology is not mature, so which is more safe or which is less safe. So in that sense, I mean, don't get into that kind of question. The key safety concern here would be safety of the passenger when, or rather the patients when they are boarding and unboarding the craft, and the safety of the craft itself when it actually is coming to take the passenger and doing its entire flight journey, it remains safe. Safe against bird strikes and those kind of scenarios actually also. Yeah.
Thank you, sir.
Thank you, Susovan. And thank you for politely muting yourself after the no. Yes.
So there is a question from Deepak, okay, regarding
I just saw
calculating CDCL, which formula have to be used for drones. I am assuming it is drones, but the formula are getting mainly for fixed wing aircraft. It is the formula same for all kind of aircraft. See, I mean, when there is a wing present, okay, the CL and CD of the wing is the way you do it actually, right? Same CL/CD for an airfoil can be used to calculate the performance of a propeller if you are trying to analyze a propeller actually. Okay. Be it, I mean, in a multi-rotor kind of environment or whatever. Okay. So again, like I mentioned, I mean, if I want to calculate this, so I am assuming that you are talking about calculating the performance of a propeller or performance of a rotor in a hovering flight, for example, because takeoff and landing. So for those things, I mean, I already mentioned, I mean, momentum theory is one way, blade element theory is another way, but that may be more complicated for you. So you can see any book on helicopter aerodynamics, and those will actually talk about hovering rotors and how to calculate the power using very simple approach. So you will get formulas in those places.
Okay. Anybody else has any questions? Ashwini, yes, definitely. Once the specific questions are over, you are welcome to ask general questions, but little bit later. We'll just wait for other students, because some students I'm sure will have some queries. They are just warming up. So, friends, we have already spent 1 hour and 15 minutes. We cannot keep on going very long. So, please.
Okay, so one new question has come, Professor Pant.
Phoenix has a question.
Yes, yes. The propeller blade configurations, we have considered only the dimensions of already existing aircraft propeller blades, which we thought could be a feasible one for ours for the calculations. Other than dimensions, we can't find any kind of further information on their blade configuration in their literature. So is it okay if we go with this, or we'll have to justify the selection of such blades? No, so I mean, I don't see why one has to restrict themselves to using existing aircraft propeller blades, because aircraft propeller blades are to be designed by you, not just selected by you. Okay. So there is no compulsion, nowhere in that, I mean, to the best of my knowledge, the design statement or the problem statement mentions that you are restricted to using existing aircraft propeller blades. So I don't know what configuration you are designing and how you are designing, and you don't have to mention that either. See, the propellers have to be designed based on the performance requirement that you actually expect from them. So you have to size them actually. You have to select, I mean, what radius I require, how many blades I want to put in that, what kind of twist I expect from that, what kind of pitch I expect from that. Is it going to be a fixed pitch propeller? Is it going to be a variable pitch propeller? So all those things actually you have to come up and say about your design. So I don't say that, I mean, or rather I will not endorse the thing that, I mean, you should look at the database of existing aircraft propellers and just select something from that. That is not justifiable. I hope that answers your question, Phoenix. Okay. Any more questions from anybody?
Yeah, the floor is open for more questions. If there are no questions, then we will open up for general questions which Ashwini ji wants to ask. So maybe Ashwini ji, you can start with your question. That may open up some students.
Thank you, Professor Pant. Now, this question I'm going to ask, I don't expect Professor Abhishek to respond to it or even to know the answer, but I'll say it anyway. And if any of the audience knows, they can always volunteer to answer this. Now, you see, when we talk of a vehicle which is, there is a transition for forward thrust, I mean, takeoff vertically and then forward thrust, and there is a transition. What kind of regulatory, control is it? I mean, you have regulations for fixed wing aircraft. We have regulations for rotary wing aircraft. But then when you have this kind of a hybrid thing, what kind of regulations govern them? Are there any regulations as yet, or they are yet to be
Sir, actually, in Europe, they have already come up, and similarly in US also they have come up already to a certain extent. I mean, EASA has done something, and likewise, FAA has already come out with this, because the entire eVTOL startup space in Silicon Valley, where there are almost 100+ startups working on eVTOL systems, they have been pushing, I mean, FAA for a long time actually to come up with the regulations. So they are, I mean, in the process of being, evolving. And some of them have already been actually put in place. So they are, of course, derivatives of, I mean, whatever are already existing for airplanes and helicopters. And some are looking at the commonality of aspects. They are trying to sort of merge them together in some form and come up. I mean, I've not actually looked at them, I mean, as such, so I don't have the details available, but it is already in process. And some of them, for example, in US, this Carter people, I mean, who are now they are actually already in process of getting their thing certified. Likewise, in Europe also, a lot of companies who are early starters, they are actually looking to get things certified.
Okay. One would expect that once the US, EASA and FAA have formulated the rules, maybe DGCA India would probably follow
Right, sir,
them.
right, sir, right.
All right.
Please expect, sir, right.
Yeah. Thank you, Professor. Very kind of you.
So your question was absolutely relevant to the topic.
Yeah,
It's
100%.
really a very, very deep insight.
Yes.
Yeah.
Right.
Okay. So students,
Thank you.
any other query or question that you have? We don't want to hold on Professor Abhishek for a very long time. Already we have spent 1 hour, 20 minutes. So I will open up the floor for next 1 or 2 minutes. If there are no hands raised or chats, then we will thank Professor Abhishek for this detailed lecture. And you are fortunate that this recording will be available to you for referring in the future.
I think just one more question is Professor Pant, that is on the same, by the same person. Okay. Regarding, do we have to deep dive into propeller blades for the task 1? Okay. So I'll let Professor Pant actually answer that part. Okay.
I have already answered on the chat window. I
you
mentioned also on the meeting that stage 1 submission is just 3-4 days away. 31st is the last date. And we appreciate that you can use some meaningful numbers, some simple numbers, but reliable numbers, justifiable formulae. Stage 2, definitely we will expect you to do a customized design for your propeller. Otherwise, it is not going to be acceptable as a feasible design. All right. I don't think there are any more questions. So I would like to officially and formally thank Professor Abhishek for very interesting and detailed talk, which will be definitely helpful for students in sizing. And I wish all the best to the students who are working on their designs. Those of you who have been given extension would be able to use the time because of the examinations, etc. For the others, we expect that on 31st, as per the deadline, Pranav is going to make a link on the website for uploading your reports. Okay, I'll once again say that stage 1 reports are limited by the size, number of pages, and also the content has to be matching with what is required in the problem statement. Do not waste your pages in giving too much survey of literature, because you have already given that in the initial concept report. I also noticed that my friend Shri Kamesh Goel is there in the meeting. He has a huge amount of experience in certification of UAVs, and recently he has superannuated from DRDO. So Kamesh, if you have some time, would you like to just unmute? Maybe you can show your video and just address the students before we go.
Hi, Dr. Pant. By chance, I have joined towards the end of it, so I do not know much of the things what has happened. Okay, so hello, are you able to listen to me?
Yes, sir, we can hear you, sir.
Yeah, we can hear you, Kamesh, no problem. No, it's really great to have someone like you on the meeting, because see, you are the one who has the maximum field experience in certifying UAVs, as far as I know. So,
That's true,
we will be taking help from you in the second stage.
Okay, no problem.
We want you to perhaps address the students on certification issues somewhere down the line, what they should keep in mind.
Okay.
So later on, we'll do that.
Do.
We'll do that later on. It's nice to have you in the meeting. Right. So we are closing to 7:30 now. I would request all of you to, if possible, show your video so that we can take some pictures. And Pranav, please be ready. You should take some screenshots if possible. Requesting you to open their cameras if possible. We'll take some pictures and then we'll close the meeting sharp. Pranav, you can take some shots right away, because it will help us. There you go. Some people are slowly opening up now. By the way, friends, I'm right now in Nagpur on the invitation of Professor Kalpit, who has just opened his video. I'm here to conduct a 2-day course workshop, and I'll be here till tomorrow night. So I'm coming to you from the hostel. Great. So nice to see the faces of some people who have been asking questions like Susovan. And Pranav, are you there? Please take some pictures.
Yes, sir. I'm on it.
Great. Take some pictures, unmute yourself if possible. And when it is done, tell us, I'll stop the meeting. In between, I lost power for a few minutes, so there might be some gaps in the recording, but I think it's fairly clear.
Okay, I think we are done.
Everybody, thank you so much. Have a very good evening.
Thank you,
And we will meet again in the next
giving the
webinar.
opportunity. Thank you so much, Professor Pant.
No, sir. So Abhishek, आप क्या बात कर रहे हो? We are so thankful to you for